My name is Paul Mattis, and I work for Microsoft. I appreciate the opportunity to make a fool of myself in as large a venue as possible. I'll say ahead of time that I tend to rush, so talking very slowly is a stretch for me. I tend to dive right into the parts that I think are cool, and all those assumptions that those parts make sense based on I cast aside. So please stop me, slow me down, ask me why the heck I'm saying something. So I'll start with usual disclaimers. I'm not actually saying anything. I'm not allowed to say anything. So I'm describing a snapshot of what I and my immediate group are working on right now. We could change our minds tomorrow. They could be changing their minds while I'm speaking. But it does definitely represent much more than slideware. This is actual work that is either in production or in pilot right now. So here is the problem. The problem is Microsoft's inter-data center network. So here's another assumption. There are at least two networks. There's a big core network, which is the external-facing network, and then there is a separate inter-data center network that just runs between the DCs. So that's where I'm working. We move a tremendous amount of data. I can't tell you how much data. It's a lot of data. And it is growing in very satisfying but also very frightening ways. So it is a continuous race to try to keep from starving the business by not having the bandwidth to move the traffic. The specific problem that we are focusing on are elephant flows. Definition is a large, long-lived stream, generally replicating things, moving huge volumes across the country or across the planet. The network is geographically diverse, and we have huge differences in latency over different parts of the network. So things like going back and forth across oceans is a very bad idea. And for that matter, doing multiple stage transactions across an ocean is a very bad idea. We also have to support different SLAs for different internal customers. So your Skype call has obviously different requirements than replicating the index for Bing. As I'm sure everyone knows, running a large network is very expensive. And the people who pay for that occasionally notice that. So optimizing the use of those expensive resources is a primary requirement. And having an unreliable network is not an option. So downtime costs a lot of money. Besides getting me out of bed, it costs a lot of money. So a solution to this is Swan. It's SDN for wide area network. There are lots of interesting published papers on this technology. It consists of an SDN controller. I left it in there. Proprietary agents running on routers, an MPLS forwarding path. And the basic idea is that at the edge of the network, you push a label on, and the controller has programmed a tunnel to get you to the other edge of the network. I have to talk more slowly. So this is a pretty high-level picture of what Swan looks like. The blue box is the most interesting one from my perspective. So that's our traffic engineering engine. That engine is supplied with topology information. It's supplied with traffic samples from the boxes at the edge. The samples are coming from IPFix or SFlow.
Is that how you're doing your elephant flow detection?
Doing what?
The elephant flow detection? The centralized TE engine?
Yes.
Okay. How are you feeding it topology data?
First generation is SNMP. Second generation, BGPLS. The section on the left is direct interaction with the hosts that are generating the traffic. I'm not going to go into a lot of detail on that today, but it does is a system that allows us to throttle applications and have applications explicitly request bandwidth before they start using it. That's not mandatory and it's not universal, but it actually works exquisitely well. It is delightful to see when we have something like a fiber cut, to see that we are successfully throttling the big guys so that the network doesn't tip over.
So can I ask, so are you seeing from an inter-data center perspective, like an SDN, obviously the SDN, but being able to use this as an SLA driven per application or like a tenant base? Does that make sense?
So what's the question?
I'm thinking like as I deploy, going to an SDN solution and having my tenants, maybe all tenants are not equal, right? Can I use this as a way to set a tag or be able to set an SLA based on that application? Give it a priority. So
Yes.
QoS.
Yes.
I mean,
So
or is that just relying on QoS to do that, or are you seeing people use this as a way to do that?
So QoS is primarily there as the final control.
Okay.
So if we do oversubscribe the network, if things are appropriately marked, then the better packets are going to get through.
Okay.
But under normal operation or under lesser emergencies, we can configure who is more important than who and decide who gets priority when we're oversubscribed.
Okay. From using this technology.
Correct.
Okay. Okay.
You dynamically provision that, or do you have a set of classes with the bottom one being like scavenger, which is whatever's available?
So we basically have two classes. We have scavenger and best effort.
Okay.
But the provisioning is static, but the allocations are dynamic. So how much of your big allocation you actually get depends on network conditions.
And is this being driven from, so I'm going to just go to a hypervisor. Are you doing it from a hypervisor perspective? Or is it within the application? Or how does it know who gets that priority?
In the particular area that I am working,
Okay.
which is a little tiny piece, so I am a senior peon, but that's about it. This is explicit application interaction. So
what do I need to
applications
run in it?
they're using an API that says, for the next N seconds, I'm going to send this much data, or I would like to send this.
Remember in the hyperscaler world, we own our applications. So when you start talking about hypervisors, we kind of look at you and go, what?
Right.
What are you talking about? What's that hypervisor thing? We don't know much about hypervisors because frankly, most of us run bare metal and we own our applications. So if the application developer wants to interact with something like this, we hand them an API and they go do it. So that's why.
So there are varying degrees of plans to either make this automatic, still not using the hypervisor level at all, just an OS driver to enforce bandwidth. And I'm sure there's someone, and I don't know who they are, thinking about that at the hypervisor level.
And so that's where I was going, is thinking at a vSwitch level.
Right. It would be useful, right?
Yes,
it would be useful
absolutely.
for multi-tenancy, less of the hyperscale type world. But
Yeah. So, and again, this is the context here is that these are Microsoft internal applications. So we own them. We have direct communication with the folks that own them, and can have explicit arrangements with them. Doing that transparently in Azure is a different space,
right.
and a cool problem, but not mine at the moment.
Because it can get very interesting.
But you could talk a lot
Oh, yes.
more about it, and you would have more to say,
Mike.
even though you don't know what you're doing with it.
You'd slow it down a little bit.
Yeah.
So I had one other quick question before we move off that slide. Just from an operational perspective, you've got your centralized TE controller. Is there one of those in each geographic region? How is that?
I do have a slide, a high-level slide on the structure of that engine, but it is redundant and scaled, and it's not hierarchical, but it is redundant.
I'll wait for the slide.
Okay. No, I always like questions that anticipate slides. It makes me look really good.
So ask more of those.
I can.
So we do have Swan deployed right now, and the next generation of Swan will be using segment routing, with the caveat that I don't make promises and nothing that I say is actually true. But using segment routing is a very good fit with this solution. So, what is the cool stuff about using segment routing in this environment? The first is vendor independence. With apologies to the nice people who ask me to speak, it is absolutely critical that we do not get locked into a relationship with a particular vendor or a particular set of vendors. So with SR being standardized and growing and more widely deployed, it is in our best interest to not get stuck. No matter how cool a particular feature set might be, it really does not have value to us unless we can have multiple vendors.
So does that philosophy also apply to Swan itself?
I'm not sure how you would.
Meaning, if Swan's developed by Microsoft, are you going to make it multi-vendor portable as well?
Well, Swan is an internal project,
Okay.
so it's a big pile of Microsoft proprietary
Okay.
stuff.
Okay. So it's not going to be like an open source project or
No.
working with other vendors.
Well, as far as I know, no.
But it could change.
Anything could change.
can change.
Another, and I will call it an advantage, is that we need to run an IGP. There are people who think needing to run an IGP is a bad thing. I happen to think it's a good thing because that gives you your basic lowest cost path routing connectivity. There is a school that says no, all we need is an eBGP mesh to connect anything together. And why do you need this extra protocol, and why do you need to understand that stuff? Even though what I work on is BGP, I think running an IGP is a marvelous thing. Basically, if your BGP goes haywire, you still have your IGP topology.
And one of the advantages also of segment routing running over your IGP is that you get the advantages, like we said before, of MPLS without having something like LDP in the middle to get out of synchronization from ISIS, create black holes.
No RSVP, none of that delightful stuff.
Very simplistic layer.
And the other nice thing that ISIS gives you is the ability to flood information transparently and for free. So being able to use BGPLS to collect everything that the IGP knows is a good thing. Specifically for traffic engineering, the ability to program only the edge of the network and not need to touch the transit nodes is a tremendous advantage. That there is no tunnel setup synchronization, tunnel teardown synchronization, no make before break logic, any of that. If you want to change a path, you program the one node that you want to touch, and it works as soon as you've programmed it, as opposed to needing to signal a tunnel, whether you're using a standard protocol or something proprietary, where you can't use it until you know that it's been successfully signaled, and that any part of that process could fail and you need to roll it back. And another big thing is that with SR, it minimizes the amount of state that we need to keep in the core of the network, and the churn of that state as the traffic engineering demands change. There should be very little state churn at all in the transit nodes. More cool stuff, which I think some of it we've already covered. So no RSVPTE, no LDP. The current core has both. We get IGP shortest path routing as our fallback. We get automatic ECMP. We get automatic local repair with TILFA. No need to configure backup paths or any of that. Something that's more recent and very interesting, which is on the OAM side, we can probe individual members of bundled interfaces. So we can diagnose those remotely. We don't have to go onto that box or use a separate OAM solution. And it lets us the future capabilities, things like BGP pairing SIDs, so that we can do egress peer engineering. So we can do cool things in data centers. And I'll anticipate some of the data center questions. I don't work with the data center folks. But having an SR-based core makes it easier in future to spread SR out towards the data centers and get some of that neat stuff working. So from 10,000 feet, we have our TE engine. The TE engine talks to something called the BGP conduit, which I will cover in more detail. It is fed topology information from a separate topology service. The conduit programs the edge of the network. The router's marked E using BGPLU, RFC 3107. The topology service gets its topology information using BGPLS and only needs to talk to one or two nodes to get that. And then we are running ISIS and SR on the network as a whole. So we're using a simple two-layer hierarchy for our traffic engineered routes. We have traffic steering routes. I think this slide is actually backwards. We have tunnel routes, which are the routes that we create with BGPLU. And our tunnel routes use /32 addresses from a dummy block that we have, dummy internal address block. And they resolve these dummy abstract addresses to actual tunnel routes, actual label stacks. And then we have traffic steering routes, which resolve an application destination prefix to one of these dummy addresses used for tunnels. The reason for this is the underlying assumption that there will be many more traffic steering routes than there would be tunnel routes, and that the churn is going to be in the tunnel routes. We will want to move large amounts of traffic along a different set of paths over time, but the individual flows that need to be moved are relatively stable. So when we want to make a traffic engineering change, we just need to change the associated tunnel routes, and all of the traffic steering routes will now be resolved over that newly redefined tunnel. So some of the pieces. There is the collectively the SDN controller, which encompasses the traffic engineering engine. And this is a scalable, highly available, cloud-based application. It operates in cycles on the order of minutes. So every couple of minutes, we evaluate another traffic engineering solution. We don't, oh, sorry, go ahead.
I was going to say, does that reevaluating, does that include crunching of your topology data every time?
It is getting a snapshot of the topology each time. It's not reacting to topology changes in real time.
Okay.
But it is.
But it is referencing that as a data.
Yep. And some of the big pieces, the traffic engineering engine, the flow collector that's getting the flow information, something called a prefix map generator, which is how we figure out what the application flows actually are, as opposed to the flow collector, which is giving us traffic volumes. Bandwidth predictor, so we're doing something more intelligent than simply getting a snapshot of the network right now. We have a trainable system that is trying to anticipate what the demands are going to be.
So you're predicting
Yes.
down the road, if I see this flow every day at this time, I'm going to automatically steer stuff this way.
Yep.
Out of curiosity, what rate are you sampling flow data? I assume it's not one-to-one.
16K, I think. And that was a big question mark on that. And then the bandwidth broker, and that's the system that interacts with the applications to explicitly request bandwidth.
What happens when any one of these components fails? We can't get the data it needs.
We still have BGP routing, right?
And does it fall back?
If the entire system falls over, then we have IGP routing. So each of these components has a different HA strategy that's specific to the component. So, for example, if we can't get topology information, the philosophy is that slightly stale data is better than no data. So we will continue for a time to use the previous iteration of the topology information. If we can't get flow information, I don't know how long we can survive. We can predict using historical data, but that's not going to be very good. And the likelihood of one of these components completely failing is fairly small, because there are redundant instances of these running in geographically dispersed locations. So if something takes out an entire data center or connectivity to half the US, as long as we have some connectivity between the control elements, we can keep running.
It's usually not failures that I think would bite something like this. It's more like these devices live in something that's on the other side of a DMZ or something, and some global firewall policy gets pushed and all of a sudden cuts off S-flow connectivity. All of your devices magically.
But we know that never happens.
Right.
In the case of
Except when
certain,
it does.
in the case of certain missing data regarding, say, for example, your elephant flow drowning out your WAN connection, wouldn't some of that be alleviated by the base level scavenger service? You could shove the elephant flow into the scavenger, and then more important things would.
Well, we would fall back to the QoS configuration,
Right.
in the worst case. So when we start dropping packets, hopefully we're dropping the scavenger traffic, and that
You're
depends on
degraded
traffic
at
on
that
marking. Right? Sorry.
You're degraded at that point, but you're not essentially DDoSing yourself.
Correct. And one of the interesting validation questions for a traffic engineering engine is verifying that it doesn't become an amplifier of bad behavior. Does this actually dampen itself? Does it converge to something sane all the time? And we have simulation technology to validate that sort of thing. More pieces. The BGP conduit, that's my piece. Basically, it is a customized BGP route reflector. It takes the proposed fib from the traffic engineering scheduler and turns that into BGPLU RFC 3107 updates to the routers. Also, its job is to keep those BGP sessions up so that those routes persist if for a time it loses contact with the TE scheduler. So we have some HA in there. It programs weighted cost multipath paths using BGP multipath and the link bandwidth extended community. Really basic stuff. It also does OAM, and I have a separate slide on that. Another piece is the topology service. Note the common bullet, scalable, highly available. They all have to be. And its job is to speak BGP-LS to a small subset of the routers and turn that into topology information that gets fed up into the traffic engineering solution. Then there is the question of OAM. And OAM is a problem. And we too, as with the previous talk, have not been happy with what's been available for SROAM. And what has been available has been vendor specific and not what we need. So we made a decision to roll our own tunnel OAM. And in this case, OAM is probably too broad a term for it. This is this tunnel up or not? So what we decided to do was to send self-ping packets from the BGP conduit through each of the tunnel paths that we want to probe. So we GRE tunnel packets to the ingress router. Under the GRE label is, or under the GRE header is the label stack that we want to exercise. And under that is a UDP packet that the egress router is going to send back to us. So it has all the advantages of self-ping in that it doesn't require any control plane interaction on any of the routers. So it scales reasonably well, and we also pull we have some of the usual wonderful BGP goodness in there are redundant copies of the conduit, so we're sending each of the routes out multiple times. So if one of the conduits dies, we don't actually lose the state in the routers. Similarly, for the OAM solution, if there's a connectivity problem with the routers and the conduit, we would have to have that same connectivity problem with all of the redundant copies of the conduit before all of them would pull their BGPLU routes, and we would lose the tunnels. And that's what we do. So when we can't probe a particular tunnel, then we simply withdraw the BGPLU route that tunnel represents. That's a nice picture of the OAM path. So didn't fit on the previous slide.
And it barely fits on that one.
But I'm losing my guaranteed 3 minutes per slide. So some issues that we have run into and some of the solutions that we have come up with. First problem is limits in label stack depth. There are two label stack depth limits in SR. One is the maximum number of labels that you can push on at egress. And the second is the maximum number of labels that a transit router can look past before it can find the IP header to do hashing for multipath. The fix for label stack depth limits is binding segments. A binding segment is is a piece of state on a transit router that says, pop this label and push on this label stack. So that now your SR traffic using your maximum label stack goes from ingress all the way down to this transit node, which then reloads it with yet more labels and out. And you can do that multiple times if you have to. So we can, the thing that the label stack depth limit constrains you on is how good a solution you can produce in traffic engineering. So being able to use binding segments lets us use better solutions. Another thing on the horizon is the BGP SRTE draft as a replacement for BGP-LU. It's a wonderful thing. You might even see my name on the draft. We can't use it until it is deployed by multiple vendors for previous discussion. But it also, it deals with a number of the issues in BGP-LU. The fact that the RFC for BGP-LU says you can push multiple labels, but nobody implemented that. They just assumed there was one label there. And we have gotten a vendor to support multiple labels, and we are getting other vendors to support multiple labels. But there are problems with that because there are implementations, senders of BGP-LU that assume the one label behavior, don't necessarily follow the convention that you have to have a bottom of stack bit, et cetera. So it's a mess. So being able to use the BGP-TE draft will help at ingress, and that is our intended solution for programming the binding segments. There's also another draft for automatically identifying what the label stack depth limitations are on the network. So we should be able to glean those with BGP-LS instead of having to simply configure that as a constraint on the TE engine. Another thing that we would like to be able to do is to have class-based forwarding. We'd like to distinguish flows based on DSCP bits. The BGP-TE draft also lets us do that, or will let us do that. And there are some very interesting issues. We don't have the ability to start over with a greenfield implementation. So as we spread this, we need to figure out how to coexist with RSVP-TE. And there were some very interesting issues there where RSVP-TE first assumes that it is the only thing that could possibly be doing traffic engineering on the network. So telling it that it can only have half of a link is not an easy thing. Having it tell us how much of the link it's using is not an easy thing. And there's also an interesting technical glitch where if you advertise the link bandwidth using ISIS, you will, whoever receives that assumes that the reason you're advertising it is because you're running RSVP. But we need that information without running RSVP. So there needs to be standards work to get that information out without the assumption. And I've run out of slides. The man in the blue, yes. Yes, the question was how deep are our label stacks? I think that with current vendor limitations, it's 4 or 5. How deep do we want them to be, besides infinite? I don't know. We would need to run more simulations to find out what the sweet spot is for, with our given topology, where the sweet spot is for getting an optimal solution. I'm assuming it's somewhere under a dozen.
Chris, you mentioned simulations just now. What do you have in place to do these types of tests, even from migration of the old Swan to Swan plus segment routing, do you have a parallel network up to be able to do simulations, or using virtual appliances? What kind of test harness do you have?
So we have a combination of limited real labs, virtual labs, some of which depend on the availability of realistic VM implementations from vendors. And different vendors are better and worse at supplying that. We also have a software-only simulation of our network, where we run our actual Swan software, but the network is simulated in software.
Are any of the components of Swan being opened up or open sourced at any given point in time?
Not that I am aware of.
That could get really interesting.
On the one slide early on, there was a notion of proprietary agents. Was that on the network device, or was that an agent on the application side communicating to that API that can do reservations and things like that?
That is a proprietary agent running on the network device, and that is a strategy that we will not be pursuing going forward.
That you are not pursuing?
No.
Okay.
So one of the motivations for switching over to SR is to not need to maintain that or put that on other boxes.
Got it. I'm just curious, what was that agent doing in the original model?
That was programming the label stacks.
Gotcha.
So the applications were talking to the switches via that.
Right. Also doing a different OAM solution. So,
Now you're just going to use the labels and.
yep. Anything else?
Just out of curiosity, how are you, come back to this topology data, because topology data is hard to do, especially if you want to crunch a very large topology using Dijkstra or something in short amounts of time. How are you processing that data on regular?
Well, the easy answer is I don't think we are.
Oh.
Because the topology is effectively configured as far as the TE engine is concerned. What we are interested in and what we call topology is link state and bandwidth utilization and label information.
Okay.
So adjacency SIDs and node SIDs and such. So very simple thing. So we don't need to figure out what the network looks like. We know. We need to know. We need to know the dynamic state of that known network. So it is not the source of truth.
You'd mentioned SNMP earlier as well, and that's where you're getting the bandwidth utilization information.
And the link state right now, yes.
Okay.
And in case nobody knows, SNMP is awful.
Is there a
No,
plan? One of these OSs that might be doing segment routing has streaming telemetry data. Are there any plans to use some of the modern ways to have the device push data straight to your platform? Or?
I'll go back to the previous answer, which is if multiple vendors will have a common solution, that would be great. But we would need a very strong motivation to write a custom agent, not on the box, off the box, to talk to each of those streaming solutions. But yes, that would make much more sense.
Even configuration, is there any significance or value in you finding having a common data model, even to configure segment routing on a device? Right now, every vendor has potentially their own data model. OpenConfig is standard for, let's say, BGP cross vendor, but I don't know where OpenConfig is for something like segment routing. Is that having any impact in terms of what you're doing?
So that is conveniently outside my area of expertise. So I don't know, but yes, that sounds reasonable, and we certainly have a lot of infrastructure around maintaining configurations.
Right.
Right now, it's CLI, automated CLI interactions, but using a database that generates those configs.
You have these 2 layers of routes that you discussed. Consider any other solutions to that problem?
That seems to work for now. So unless someone identifies a a compelling reason to do something different. That's,
So there's nothing competing with that concept then?
no, it seemed a reasonable way to organize it right now. I think we will learn more as we deploy more of this, and it would be nice if we could learn more by simulating more of this. But yeah, right now that's fine.
It really sounds like the tunnel routes are like an FEC. And then you just put a bunch of flows in that FEC. And
Yes.
And did you say this is supported by, was it DSC or whatever? Did you mention desired state configuration from that you can use on Azure and stuff like that?
No, it's not. It's not using Azure stuff right now.
Okay. Okay.
That can change too. Well, I'm in the Azure group because networking is under Azure, but the integration of that is not complete.
what else would you like OAM to do? Like what are the top couple of items that?
So we would like to be able to use the labels that let you select members of lags, so that we can use that to take a link out of a lag if it's failing. That's the first thing.
Okay.
There have been suggestions of making the OAM service available for other uses besides validating tunnels. So latency measurements, for example, would be a wonderful thing. Right now, we don't have plans beyond just is the tunnel up.
Have you thought about adding instrumentation to your self-pinger to do that for all the hops along the way?
Thought about it, sure.
Okay.
Did you say currently it does not remove a link that's degraded or down?
An individual, it will take down a tunnel if the current entire stack, the entire path is broken.
Okay.
And next step is adding additional probes to get the individual members of the lags that feeds back into a different system to take the link down.
Okay.
We would still leave the tunnel up because it's still usable.
But make it a lower priority to go out that route.
Seems like a lot of this relies on getting the metrics off the boxes to figure out through all these different components what paths should be engineered and that kind of stuff. And it also seems like that might be something that more data is better, but that's probably not actually the case, right? Because if you get data from conflicting sources, then you have to figure out a way to. I'm trying to think, like, it seems popular now to offload some of the analytics to a different engine on the network, right? So in addition to getting metrics off the box, you could also get it from a different source. But more data in that case probably isn't a great idea, because what if you get conflicting, like, there has to be some way to
Arbitrate.
compress that stuff and figure out what the real. So is that something you guys took into account, was, we only want the data from one place and this is the source of truth?
Are you talking about flow data, topology data?
Like flow data mostly, I guess.
Okay. So I guess the trick is to figure out what the right amount is,
Right.
so that we can make a good but frequent decision. And clearly we can do interesting things with prediction and offline analysis, rather than trying to figure out during the regular iteration, trying to improve the quality of that data. I guess the answer to your question is maybe.
Yeah.
Maybe dumb question. You keep coming back and mentioning lag. All of this can be just ran across ECMP though, right? So what's the purpose of lag in this environment?
Because we and I don't know why. So, but most of our links are lags.
Okay.
We will run ECMP across geographically diverse links, but we don't tend to do ECMP over the individual members. If they really are equal cost, then we just turn them into a lag.
That, are you running those lags into different, like in a stack or something, so they're on different blades, in a chassis, or on
I don't know.
different parts in a stack? That's one reason